More than 4.5 billion years ago, the Milky Way galaxy collided with a nearby dwarf galaxy. This encounter hastened the formation of stars. Our solar system is a part of the Milky Way galaxy. Within the solar system, material circulation had been progressing. The water component from the outer region evaporated to make materials dry. Through this process, particles were zonally distributed depending on their water content. The bipolar flow stopped, and with it, material circulation. Some regions around the Sun with high particle density appeared. Within these regions, collisions frequently occurred. Small particles gradually grew to become planetesimals. Planetesimals continued colliding with smaller particles and other planetesimals, eventually growing to planets such as the Earth. A number of planets were moving in the same orbit. The early Earth collided with a smaller, Mars-sized planet. Debris from this impact eventually came to form our Moon. The Earth-Moon system, as we know it today, was in place. Countless planetesimals and icy planets bombarded the early dry Earth. Due to the bombarding water-enriched planetesimals, the Earth became enveloped by an ocean atmosphere system. Water vapor in the atmosphere produced rain, forming an ocean. The atmospheric pressure gradually decreased. The carbon dioxide-rich atmosphere transitioned into a CO2 ocean covering the water ocean. Carbon dioxide also combined with rock components and was transported to the bottom of the ocean through weathering and erosion. At this time, the ocean was still toxic with a high salinity and an overabundance of metals. It was too toxic to support life. Upwelling mantle displaced the oceanic plates above. Uplift of the plate by mantle convection caused horizontal slippage due to the weight of the plate. This is plate tectonics in action. The oceanic plate subducted under the lighter continental plate. Weathered sediments neutralized the ultra-acidic ocean. Heavy metals settled out and became fixed as deposits at the mid-ocean ridge. These deposits were transported through plate tectonics into the deep mantle. Gradually, the ocean became a habitable environment. By 4.2 billion years ago, a liquid core formed in the center of the Earth. Convection within the liquid core created a strong magnetic field surrounding the Earth. This geomagnetic field shields the Earth's surface from cosmic rays. The Earth's surface was nearing readiness for life. The early Earth, when the atmosphere prevented sunlight from reaching the surface. Primitive life was about to emerge underground, in the cave of a geyser. Uranium ore emitted large amounts of radiation, creating a diverse range of materials, and eventually producing the early building blocks of life. Water boiled and rose up to the surface, and the surface water flowed back down into the natural nuclear reactor. The temperature of the geyser water remained below 100 degrees, protecting the newly formed biomolecules. The underground environment was reductive, while the surface environment oxidizing. These conditions were necessary to synthesize biomolecules. In the Earth's Hadean eon, tidal forces were much more pronounced than they are today. Even lakes had significant ebb and flow of water, creating wet and dry cycles. These wet and dry cycles were one of the most crucial factors in producing the building blocks of life. Fatty acids came together, encasing the proto-life molecules. Polymerization progressed under the wet and dry cycles. Eventually, protein-like basic materials that could act as catalysts were produced. These molecules circulated between the geyser cave and the surface environment. The interactions of these materials led to more complex biomolecules. Proto-RNA combined with enzyme-like basic materials and evolved into ribozymes, which had the ability to replicate themselves. This laid the groundwork for life to reproduce. Finally, these molecules were enclosed within lipid membranes, forming primitive protocellular life. This was the beginning of life. The Earth's plate tectonics, which had begun with the creation of its ocean, eventually destroyed its primordial continent and subsumed it to the deep mantle. By 4 billion years ago, the mother continent had disappeared, leaving life on the margins of a fragmented landmass. Inside the Earth, a dramatic change was about to begin. The subducted primordial continent descended toward the core mantle boundary. The wealth of radioactive elements in the primordial continent caused the uppermost part of the core to melt. By 4.2 billion years ago, the newly created liquid outer core was strengthening the Earth's magnetic field, protecting the surface environment against solar winds and cosmic rays. As a result, life could exist on the surface environment. The supply of energy and nutrients through material circulation is necessary for life. The essential mechanism to maintain life is an endless flow of electrons. The first proto-life couldn't survive very far from the nuclear geyser due to insufficient energy. Mutations, however, allowed life to evolve. The more resilient life forms were able to adapt and survive in harsh environments. This second stage of proto-life evolved to make use of the sunlight available on the Earth's surface. They developed a metabolism that converted light energy into electrochemical energy. Moreover, they used sugars to store energy for the sunless night hours. The source of energy for life on Earth shifted from nuclear geysers to the sun. Around 4.1 billion years ago, the ocean was still extremely toxic, killing off most of the proto-life forms within it. Nevertheless, some proto-life forms survived the extreme environment. They developed protective mechanisms to prevent the metallic ions in the ocean water from entering their proto-cells. This proto-life began coalescing into larger and more complex forms. Modern life forms use only 20 kinds of amino acids. This means our ancestors that used the same amino acids were the ones that survived the mass extinction. Evolution walks a perilous tightrope between continuing and ending. Unstable RNA evolved through ionizing radiation into more durable DNA, making it possible to reliably pass information across generations. And the third stage of proto-life was born. This was the beginning of prokaryotic organisms, the ancestors of today's archaea and bacteria. Oxygen, when unbound to any other material, can be toxic to life because oxygen destroys the reductive life body. Therefore, the first photosynthetic organisms would have been anaerobic microbes, which produced no oxygen. Life, however, adapted, taking advantage of oxygen. As a valuable source of additional energy. This development resulted in the appearance of cyanobacteria. Cyanobacteria produced oxygen, which crystallized into felsic iron-bearing oxide, reducing the iron content of the ocean. Still, the ocean was 5 times as saline as it is today. As the Earth's interior cooled, old slabs of the primordial crust, resting at the bottom of the upper mantle, fell into the lower mantle. Meanwhile, numerous mantle plumes ascended from the lower mantle into the upper mantle. This phenomenon is known as mantle overturn. Mantle plumes pushed the basaltic crust upward, generating landmass. This created shallow marine environments penetrated by sunlight, which allowed the cyanobacteria to flourish. The oxygen produced by the cyanobacteria gradually altered the Earth's atmosphere. On the ocean floor, ferric and ferrous iron were accumulating in the form of hematite and magnetite, creating a massive banded iron formation. By 2.5 billion years ago, the remaining banded iron formation was a few kilometers thick. This rapid decrease in iron content changed the color of the ocean to a familiar blue. Life began to change the surface environment. Such is the coevolution of the Earth and its inhabitants. This was an important step in life on Earth's long journey toward civilization. A collision between the Milky Way and a nearby dwarf galaxy produced countless glowing stars. Within a few thousand years, some of these stars ended in supernova explosions. A myriad of cosmic rays from the supernova deteriorated the Sun's heliosphere and bombarded the Earth. These cosmic rays helped generate cloud condensation nuclei, which produced more and more clouds until the Earth was completely blanketed with them. The thick cloud cover prevented sunlight from reaching the surface of the Earth. The Earth underwent a global glaciation event known as the Snowball Earth. This caused another global mass extinction. But once again, some life survived yet another difficult period beneath the ice sheet. Tiny life was protected by the Earth's massive circulating system. And the Earth is similarly held in place by the solar system and the expansive universe. Life is but one part of an enormous system.